Welcome to this video on cooling towers, key components of many HVAC systems that make efficient use of evaporation to reject heat to the environment. Here's what we'll cover in this video. First, we'll explore the basic foundation of cooling towers. Then we'll examine different types of towers and how air and water flow through them. And finally, we also look inside a tower to understand its critical components. By the end of this video, you'll be able to explain how evaporative cooling works and how water interacts with air to remove heat. You'll also be able to describe how various types of cooling towers function and differ, especially mechanical versus atmospheric systems. Think about this. Why many large buildings and industrial facilities rely on water-cooled systems instead of simpler air-cooled ones? Think what are the differences that make this to happen? In this video, you'll find the answers by exploring how evaporative cooling helps save energy while improving performance. Cooling towers are heat rejection devices that remove heat from water by allowing a small portion of the water to evaporate into an air stream. This principle is the cornerstone of many industrial and large commercial HVAC systems. You'll most often find cooling towers connected to water-cooled chillers or absorption systems. These systems rely on a continuous cycle of heat exchange, and cooling towers provide an efficient passive way to release excess heat to the atmosphere. The efficiency of this process is rooted in thermodynamics, especially the latent heat of vaporization. As water evaporates, it absorbs a large quantity of energy, significantly reducing the temperature of the remainder water. Since this cooling allows the water temperature to approach the ambient wet bulb temperature, it's far more efficient than simple cooling systems. Cooling towers are broadly classified into mechanical draft and atmospheric types. Mechanical draft towers use fans to move air. In forced draft, the fan is at the base pushing air upward. In induced draft, it's at the top pulling air through the field. Atmospheric towers operate passively. They use a natural convection where heated air becomes less dense and rises, drawing cooler air through the field without mechanical assistance. This type is more common in older or less energy-intensive applications. In terms of flow arrangement, we distinguish between counterflow and cross-flow designs. In counterflow towers, air moves upward in opposition to the downward water flow, providing efficient heat exchange. In cross-flow towers, air moves horizontally across falling water, offering lower pressure drops but slightly reduced efficiency. Each configuration has advantages depending on the application and the available space. Let's now take a closer look at the internal layout of a cooling tower. It typically includes components like spray nozzles to distribute warm water, fill material to enhance contact with air, and drift eliminators to reduce water loss. The fill or packing is particularly important. It consists of structured plastic sheets or similar media that offer a large surface area. This facilitates the evaporation process by maximizing water-air interaction. In large towers, a structure is divided into individual cells, each with its own fan and flow control. This modularity helps meet varying heat rejection demands efficiently while minimizing interference or recirculation between sections. Here we see a schematic of a cross-flow cooling tower. Warm water enters at the top and is distributed over the fill material, while air enters horizontally from the sides. This cross pattern, air moving sideways and water falling vertically, gives the tower its name. The interaction between air and water within the field promotes evaporation, cooling the water. The cool water then exits at the bottom and returns to the system. Notice also the presence of drift eliminators and a fan at the top, which help drive airflow and minimize water loss. To summarize, cooling towers relied on evaporation to cool water effectively, using the latent heat of vaporization to operate near the well bulb limits. They can be classified based on airflow method and geometry, with mechanical versus atmospheric and contraflow versus crossflow configurations. And their performance depends on the internal structure, especially the fill, drift eliminators, and fan arrangement. To deepen your understanding, you'll want to study psychrometrics in detail, how humidity and enthalpy affect cooling potential. We'll also explore performance metrics like range, approach, and capacity in the next video. Finally, look at how cooling towers are selected and sized in real engineering projects, considering not only performance but also water use, noise, and space. Thanks for watching this video.